Okay. And we're back. So now we're going to talk about heat exchange between the system and the surroundings. That exchange is going to occur whenever the system and the surroundings have a different temperature from one another. And the temperature is the way we're going to measure the thermal energy difference between those two things. Heat is going to flow from whatever material has the higher temperature to whatever material has the lower temperature until both of the objects have the same temperature. And at that point, where the temperature values are the same for both of them, that is called thermal equilibrium. Thermal equilibrium is a way to think about the final temperature of a reaction between the system and the surroundings. We are able to sort of track the amount of heat absorbed by material using what's called the heat capacity of an object. The heat capacity of an object is the temperature increase of the material. The temperature increase that's related to a particular amount of heat that it's absorbing. Okay, so if you think of a system and that system is absorbing heat, right? Though there's going to be a particular temperature change that's associated with the absorption of that heat. All right, if that makes sense. So if you look, let me get my little pen thing. All right, so if now this might make sense then. So the larger the heat capacity of an object, the smaller the temperature change is going to be for a particular amount of heat. So if you can imagine, say that we're looking at a Q value, okay, and Q is the heat value, and you have something with a heat capacity of 1 and something with a heat capacity of 10. Ooh. So stupid looking. Okay. Now, imagine that this Q value is 100 joules, okay? So the thing with the higher heat capacity is going to have a smaller temperature change, right? Because 10 times 10 is 100. The material that has the smaller heat capacity, a heat capacity of 1, right? The temperature change for that would have to be 100 for it to have 100 joules of heat. So you see the heat capacity of an object is related to the temperature change of that object. Right? So the heat capacity is going to depend on the amount of material, right? And we usually measure heat capacity by mass. The only thing that heat capacity depends on is, well, not the only thing, I guess. The only thing that it's going to depend on is the amount and the type of the material. So both of those things. Different materials are going to have different heat capacities because things are able to absorb heat at different, or to different extents, I think is a better phrasing there. But then when you're looking at a particular material, the amount of heat it's able to absorb is going to differ based on the mass of the object. Okay, anything that is mass dependent or amount dependent, remember that's called an extensive property. So heat capacity is an extensive property. Okay. So again, just looking at the specifics, 200 grams of water is going to require twice as much heat to raise its temperature than 100 grams of water. All right, so it's mass dependent. Now, if you're looking at two different substances, though, if you have 100 grams of sand and you have 100 grams of water, the masses of those two things are the same, okay? But the internal heat capacity of both are different. So sand is going to have a 12-degree temperature change. Water is only going to have a 2.4-degree temperature change. And if we think back to the previous slide, that probably means that water has a larger heat capacity than sand does, right? So that the temperature change is not going to be as dramatic for something like water as it is for sand. Okay. Now, a slightly different term that we're going to look at, hopefully it makes sense though, the name of it, is not just heat capacity, but specific heat capacity. Okay, so specific heat capacity, that has to do with a particular material's ability to absorb a specific amount of heat. Okay, before we were talking about with heat capacity in general, how the amount of material will change the amount of heat something's able to absorb. Well, the definition of specific heat capacity is the amount of energy required to raise the temperature of 1 gram of any material by 1 degree Celsius. All right, so now we've specified the amount of material that we're looking at. So because we have defined this idea in terms of mass and in terms of temperature, this is no longer an extensive property, okay? The specific heat capacity of something doesn't change when you change the mass of that thing. You can have a gallon of water or 1 glass of water, but all of the water is going to have the same specific heat capacity. Whereas if you have a gallon of water and a glass of water, the heat capacity of a gallon of water would be larger than the heat capacity of a glass of water. Okay, so specific heat capacity is an intensive property, and that's because it's more like a ratio. Okay, we're saying joules per gram degree Celsius. So we're breaking it down. Okay, we have another type of heat capacity, which is molar heat capacity. That's another intensive property because it's joules per mole degrees Celsius. So as soon as we have a specified amount within that unit that we're looking at, that turns the property from an extensive one to an intensive one. And this is just a list of some common heat capacities. You do not have to memorize these, of course, but you need to be able to use them and to understand what they mean. And you should be able to look at this list of heat capacities, specific heat capacities, and start to make kind of associations. Like you see how high the specific heat capacity of water is. It's much higher than anything else. That means that water is able to handle large amounts of energy absorption with very little temperature change. Right? We are going to use the specific heat capacity of an object to help us figure out how much heat is being released or absorbed by a certain material, okay? The relationship between heat and specific heat capacity is this relationship down here. And you guys will hear it a lot as Q equals MCAT, okay? That MCAT is mass times specific heat capacity times delta T, which is our temperature change. And just like every delta, that means final temperature minus initial temperature. All right, so let's think about this for a second. Suppose you're cold weather camping, you decide to heat some objects. To bring in your sleeping bag for added warmth, you place a large water jug and a rock of equal mass near the fire. Over time, both the rock and the water jug warm to about 38 degrees Celsius. If you can bring only one into your sleeping bag, which one would you choose to keep you warmer? And why? So think about this for a second. Okay. So hopefully this kind of makes sense to you. The water is going to release more heat as it cools. That has to do with a specific heat capacity of water. Okay. Let's look at another type of calculation here. Suppose you find a copper penny. How much heat is absorbed by the penny as it warms from the temperature of snow, which is -8 degrees Celsius, to the temperature 37 degrees Celsius. Okay, and we get here the heat capacity, a specific heat capacity of copper is 0.385 joules per grams degrees Celsius, and the penny has a mass of 3.10 grams. So sort out your process here first, okay? Think this out. This just goes in steps like anything else. Step one, I would probably write out my formula, and I would write out the things that I was given in the problem, the information that I know, okay? So I know the mass of the penny, I know my initial temperature, I know my final temperature, I can find my delta T value, which is again, final minus initial. And then I can use that information, I can plug it into that Q equals MCAT equation. Okay, so when you do this, now look at these units also. You have 3.10 grams times 0.385 joules over grams degrees Celsius. So right away we see that our unit of grams cancels out. Now we multiply that by 45 degrees Celsius, and we see that our degrees Celsius cancels out now. So we end up with a heat value of 53.7 joules. Okay. Like I said before, when you have these two objects at different temperatures and they are placed in contact, so they start to transfer thermal energy, you're always going to have the heat flow in the direction of higher temperature to lower temperature. Now, whatever amount of heat is lost by the warmer thing, that is the exact amount of heat that's going to be picked up by the colder thing. So these numbers are related. So we're looking at this beaker down here as an example. Now imagine that that metal was heated up, okay? And then it's placed into that beaker. The heat from the metal is going to transfer into the water, right? Because the water is at a lower temperature. Whatever amount of heat transfers from the metal to the water, see how numerically those numbers would be the same value? They would just be like opposite signs. Whatever the metal loses, that's exactly what the water gains. So that's why we have this relationship here between the Q of the system being equal to negative Q of the surroundings. So whatever the system loses, that's what the surroundings gains. It's always going to be that opposite relationship. Okay, so with that in mind, take a minute to look at this question. All right, I'll give you a minute to read it. Okay, now the main thing we're looking at here is that we have two important parts of this relationship. Okay, we have the mass of substance A is twice the mass of substance B, and we have the specific heat capacity of B is twice the specific heat capacity of substance A. All right, so we have this multiple of 2 that is, I don't know, it's associated with each substance, right? So substance A is 2 times the mass of B, specific heat of B is 2 times the specific heat of A. When we think about Q equals MCAT, that means that the final temperature that's going to be reached between the two of them is going to sort of be like a cancellation, right? That final temperature value is going to be exactly in between the temperatures of the initial substances, right? Because they are losing and gaining temperature the exact same way. Okay, so let's look at this one. A 32.5 gram cube of aluminum, initially at 45.8 degrees Celsius, is submerged into 105.3 grams of water at 15.4 degrees Celsius. What's the final temperature of both substances at thermal equilibrium? And now we have the specific heat capacity of aluminum here, which is 0.903 joules over grams degrees Celsius. And we have the specific heat capacity of water, which is 4.18 joules over grams degrees Celsius. Now, if you want, hit the pause button right here and try to work this problem out on your own and see where you get. I'm going to work through it now, but I really would recommend you taking the time to try it out on your own. So the first thing you want to do is you want to organize your information, see what your formula looks like, right? So what we want to remember here is that we have that situation where you have a metal being submerged in a beaker, right? So there's going to be an opposite relationship between the Q of the water and the Q of the metal. Now I have the negative sign in front of the metal here. It doesn't really matter which material you put the negative sign in front of. I just have it in front of the metal here. Okay. And Q is always going to be equal to mass times the specific heat times the temperature change. So Q of the water is going to equal negative Q of the metal. Now, which pieces of information do we know for each of these materials? Okay, let's tick this off one by one. All right, we know the mass of the water. We know the specific heat of the water. We know that delta T means final temperature minus initial temperature, and we do know the initial temperature. Okay, we're going to keep our negative sign right here. Then we know that the mass of the metal is 32.5 grams, the specific heat of the metal, and we know that the initial temperature of the metal was 45.8 degrees Celsius. All right, now what we are left with as our unknown is the final temperature of both objects. Okay, and the final temperature value is going to be the same for both materials because thermal equilibrium is our final temperature. So this just becomes a little bit of an algebra problem. All right. So we want to, well, I can show you how I solved the problem, which was the first thing I did was multiplied my mass and my specific heat values and turn them into just one number. Oh, sorry, that line went a little crazy. And then once I had those values as one number, then I distributed into my second set of parentheses. And that TF, my final temperature, you can also turn that into an X value if you wanted to. But what I end up with over here is basically 440.154 times X minus 6778.37, and that equals negative 29.3475 X plus 1344.12. Okay, so now I want to get my two X values on one side, and I want to get my non-X values on another side. So you're going to see what happens in this next step is I'm going to be adding this value over here to 1344, and I'm going to be adding this value over here to 440.154. Okay. And when I do that, I get 469.502 times delta T, or times final temperature, not delta T. And again, that's my X value, and that equals 8122.49 joules. Now I'm going to divide both sides by that numerical value that's in front. Okay, so I'm going to divide both sides by this number, 469.502. And then I'll get my final temperature value, which is 17.3 degrees Celsius. Okay, hopefully that makes sense. So now try this one out on your own. Hit the pause button because I'm going to go ahead and put the answer up, but I would like you to try it on your own. Okay, there's the formula. Q of the water equals negative Q of the metal. Plug in all the material. In this case, our mass value for copper is our unknown. And when we solve it out, we get 37.8 grams. You'll find doing these calculations that if you forget to put this negative sign in over here, a lot of times you'll end up with a negative mass value or you'll end up with the wrong sign at the end, okay? And that's because one of the materials is always going to have a negative temperature change, okay? So this little negative sign up here helps counter the negative sign that you have over here, okay? That's what gives you this positive mass value at the end. All right. We have what is called pressure volume work also when we're talking about these energy transfers. And that's going to be the work that's done by something like a gas as it is expanding over an external pressure that's constant. Okay, so you can imagine in this, you can visualize it in this picture down here. You have this system that has one of the cylinders with a piston in it, right? So as a gas expands, it can push up. Wow, imagine that's an up arrow, but it can push up, all right? And when it pushes up, it can actually increase the volume that it exists in, all right? So that relationship is a type of work that's done. So the work that's being done by the gas there is measured by the volume change, delta V, final volume minus initial volume, times the negative external pressure. All right? You're like, why does this matter? How is this important? But it is, because heat and work is what determines energy exchange, right? So one way that we're going to be able to calculate the work that's being done is by looking at the volume changes of a system. When we do find the volume change of a system, you're going to notice that in this formula, let's change a color again, work equals negative pressure times delta V. Well, the units of pressure are atmospheres. The units of volume are going to be liters. Okay, so we need to be able to relate that back to joules, which is our common energy unit. So it turns out that 1 atmosphere times liters is equal to 101.3 joules. That is a number that you have to know. Okay, so star that, highlight it, memorize that one. Because you're going to need it to be converting this pressure volume work into units that you can use to calculate energy changes. Okay, so here's an example of this. A cylinder with a piston expands from a volume of 1 liter to a volume of 2 liters against an external pressure of 1 atmosphere how much work in joules was done by the expansion. So you know that work is negative pressure times delta V. So that means it's going to be negative 1 atmosphere times 2 minus 1, so times 1. So you end up with negative 1 liters times atmospheres. So now we have to take that value, negative 1 liters times atmospheres, and multiply it by 101.3 joules, right? That's our conversion right there. When we do that, we get a work value of negative 101 joules. Okay? Let's look at another example here. To inflate a balloon, you must do pressure volume work on the surroundings. If you inflate a balloon from a pressure of 0.1 liters to 1.85 liters against an external pressure of 1 atmosphere, how much work is done in joules? So you break this up into steps, okay? First, I'm going to find my delta V. That's going to be final minus initial volume, so it's 1.75 liters. Then to find my work, I'm going to take 1.75 liters, multiply it by negative pressure, so negative 1.00 atmospheres. So I get a value of negative 1.75 liters times atmospheres. Now I want to convert that from liters times atmospheres into joules. Okay, so there's my conversion. And I end up with a work value of negative 177 joules. Right, so it's pretty straightforward. So you can imagine if we know that delta E is Q plus W, that, you know, we can always, hold on, let me get my little pen out again. All right, so if we could measure these two values, then we could calculate delta E, but it's not always easy to measure those values, right? So what we can do is that if we have a system where there's no change in volume, right? So delta V is 0, that means that work would be 0, right? Because if you think back to your formula, work equals negative pressure times delta V. If delta V is 0, then when you multiply the pressure by it, you're going to get 0. So if we did that, then our formula up here, delta E equals Q plus W. If we held the volume constant and work is 0, then we can relate delta E of our system directly to the heat of our system, right? So we need a way to be able to measure temperature change at a constant volume for us to do this. Okay. And the easiest way to do this is using what's called a bomb calorimeter. Okay, so our bomb calorimeter is, I think there's a picture of it somewhere, maybe in the slides, but definitely in your textbook. And it is a rigid insulated container. Okay, it is filled with water and it's sealed. Now, because it is such a rigid container, when the reaction happens, there will be no volume change in that reaction. All right, so the temperature change that we're going to measure, that Q value, is going to be directly related to that delta E value. Also of note is that the Q of the surroundings, which would be your water in this case, that's going to be equivalent to the Q of your calorimeter. Okay, so these two things are going to be synonymous in this scenario. And we have to remember that whatever we're measuring in the water, that's going to be the opposite of what's happening to our system. Okay, so the Q of the system is going to be opposite the Q of the surroundings. Oh, good, there's a picture of it. So you have this really rigid container here. Okay, The surroundings here are filled with water, different color. And this will be your reaction chamber. Okay, so we're going to measure the temperature of the surroundings, right? That's the easiest place that we can measure the temperature. It's a lot easier having a thermometer placed in the water that's surrounding the reaction than it is to try to get a direct measurement of what's happening right inside of the sample chamber. It's not logical. And we know that there's going to be a relationship between the water temperature and the sample temperature, so there's also no reason to do something that's more difficult. The wire that's going to come in here is going to cause the sample to combust, and then we're going to be able to track the temperature change that happens. Okay, when we're calculating delta E values using a bomb calorimeter, we are going to be using the heat capacity of the calorimeter. Okay, not the specific heat capacity, the regular heat capacity. That's also called the calorimeter constant. All right, so remember what we said about the heat capacity versus specific heat capacity. Heat capacity is an extensive property and it's amount dependent. All right. These are the units for our calorimeter constant. They're usually in kilojoules per degree Celsius because the amounts of energy are higher. But joules or kilojoules are both reasonable ways to report the calorimeter constant or the heat capacity. So let's look at this in practice, okay? And again, if you guys want to hit pause and try it, you can, but we can work through this one together. So you have 0.1010 grams of sucrose that undergoes combustion in a bomb calorimeter. The temperature rises from 24.2 degrees Celsius to 28.33 degrees Celsius. The heat capacity of the bomb calorimeter is 4.9 kilojoules per degree Celsius. I'm going to define delta E of the reaction for the combustion of sucrose in kilojoules per mole of sucrose. Okay, so we have to be really careful with the wording here. We are given information in this problem, and we are going to be able to calculate a delta E value. But the delta E value that we're going to be calculating is going to be for this specific amount of sucrose. Okay? The final answer that we're looking for here is going to be the delta E for the reaction in kilojoules per 1 mole of sucrose. So those are two different things, and we have to be very clear about that. But let's find what we can find with the information that we're given. All right, we'll start there. So our step one, we're going to be finding the Q of the calorimeter itself. This equation for the Q of the calorimeter, please know it, okay? You're going to notice that for Q cal, there's no mass value, okay? That's how you know you're not using the specific heat. Q equals MCAT. That equation involves the specific heat value. But Q of the calorimeter does not have a mass value in the equation because you're only using the heat capacity, right? And there's no mass unit in heat capacity. So to find the Q of the calorimeter, we're going to take the heat capacity of the calorimeter and we're going to multiply it by the temperature change, final temperature minus initial temperature. And we're going to get a Q of the calorimeter of 16.7 kilojoules. All right, that's great. Next step, we need to relate the Q of the calorimeter to the Q of the reaction, right? And we remember that we have that opposite relationship there. So whatever my Q value of my calorimeter is, negative Q cal will be the Q of my reaction. So my Q cal was positive 16.7 kilojoules. My Q of the reaction will be negative 16.7 kilojoules. Right? Now I need to find the E for my reaction. Well, this 16.7 kilojoules was true for 1.01 grams of the sucrose. Now I need to know how much heat would be given off per mole of sucrose. Okay, so my E of the reaction is going to be, I'm going to write this out terribly right now. Right, I'm going to do like a kilojoules, which is my negative 16.7, and I'm going to divide it by the moles. Wow, that's an M-O-L. So it's kilojoules over moles. So I'm going to take my 16.7 kilojoules and divide it by the moles of sucrose that I'm going to find by doing this calculation right here. Okay, so it's just the mass of the sucrose, and I'm going to divide it by the molar mass of sucrose. That's going to give me moles, right? You're just going to use your periodic table, like the standard practice for whenever we're going from grams to moles. When I have my mole value for sucrose, then I can take the kilojoule value, divide it by the mole value, and now I have a delta E value of the reaction in kilojoules per mole of sucrose. Okay. Now, finding delta E is different than what's called enthalpy. Okay. Enthalpy is given the designation H, and that is actually the sum of these two values. Pencil. It's the sum of the internal energy, and it's the sum of your pressure and your volume. Okay. Enthalpy itself is a state function. Okay. And remember, state function means that the process doesn't matter. It's only final minus initial. Like that change between final minus initial is what matters. Okay. So enthalpy change, or your delta H value, that's going to be the heat of a reaction when your pressure is constant. Okay. So when we have constant volume, we can find the Q of a reaction using your calorimeter. But to find the enthalpy of a reaction, we need to find the Q value, that heat value, at a constant pressure. Right? Star that, make it very clear to yourself that that's true. So let's look at the difference between those two ideas. So you have this example here. Lighters are fueled by butane. When 1 mole of butane burns at constant pressure, it produces 2658 kilojoules of heat, and it does 3 kilojoules of work. What are the values of delta H, which is enthalpy, and delta E for the combustion of 1 mole of butane? Okay, so think about that for a second. All right, and then let's think about why this is true. Delta H is equal to Q at constant pressure. So we were told that we have this system at constant pressure here. So whatever this Q value is, it produces 2658 kilojoules of heat. That's your Q value. So your delta H value has to be equal to your Q value. But your delta E value is equal to Q plus W. Okay, so if your system does 3 kilojoules of work, you're going to have to subtract that work value from the Q value in order to get your delta E value. All right, so that's the difference between those two. Okay, now we're going to talk about what the signs associated with delta H mean. Okay, we have two types of reactions. One is called an endothermic reaction and one is an exothermic reaction. When your delta H value is negative, that means you have heat that is being released by your system into the surroundings. Okay, exothermic reactions give off heat. Your surroundings get warmer. So if you were holding like an exothermic reaction in your hand, like those chemical hand warmers we were talking about in the last lecture presentation, you would feel the heat that was coming off of that reaction because the reaction is exothermic. The products of that reaction are going to have less chemical energy, less potential energy than the reactants. And because we have to make sure that we're not gaining or losing energy, the difference in potential energy between the reactants and the products gets released as heat. Okay, that's an exothermic reaction. Heat is exiting the system. All right, the opposite of that is called an endothermic reaction. In an endothermic reaction, heat enters the system. Okay, an endothermic reaction has to absorb heat in order to proceed. If you're holding an endothermic reaction in your hand, it would actually feel cool to the touch because it would be absorbing the heat from the surroundings. All right, and this is because the products of an endothermic reaction have more energy than the reactants. So in order to create those products, the reactants would have to absorb energy from the surroundings to do that conversion into products. Okay, so if you have an endothermic reaction occurring in the flask, what happens to the temperature of the flask? Take a second. Hopefully this makes sense. The temperature would fall or decrease because the reaction itself would be absorbing heat, and you would be monitoring the temperature of the surroundings in the flask, usually of the water that's in the flask. The temperature of that water would go down as the reaction itself absorbed the heat. Okay, take another minute, pause this a second, answer these questions. I'm going to keep going through them, but you should take the time to answer them yourself. We have 3 processes here, and you have to figure out whether they're endothermic or exothermic and whether they have a positive or negative delta H. Okay, so first we have sweat evaporating from skin. Well, if we have sweat evaporating from skin, what do you think that process is? If you have sweat evaporating, right? That's going from a liquid. Sweat is going from a liquid to a gas. For a liquid to turn into a gas, that's going to require it to absorb heat and vaporize. If the sweat is absorbing heat, that means that it's an endothermic process. Okay? If it's an endothermic process, the delta H has to be positive. Water freezing in a freezer. Well, if water is freezing, that means that the liquid water itself is going to be releasing heat, releasing its own heat into the surroundings, right? And the refrigeration, like it says here, the refrigeration system in the freezer is going to remove that heat in order for that freezing to continue. An exothermic reaction will have a negative delta H value. For wood burning in a fire, this hopefully is the most straightforward one. The process of burning is always going to release heat. The release of heat is by definition exothermic, which would also have a negative delta H value. Okay. The next thing we want to talk about is the relationship between the amount of reactants and products we have and the amount of heat that is released or absorbed. Okay. It turns out that the enthalpy change of a reaction is an extensive property. And I mean, this should make sense logically also, because that means that the more reactant that you use, the bigger the enthalpy change is going to be. So for this example below, we're looking at the combustion of propane, right? So what they're saying here is if you have 1 mole of propane gas and you burn it with 5 moles of oxygen, it's going to release this much heat. Okay. So it should make sense of you then that it should make sense to you then that if you had more propane, say you had 5 moles of propane, that you would release 5 times the amount of heat from that. Okay, that's what makes enthalpy an extensive property. The more reactants you have, the more heat you're going to produce, and vice versa. All right, and that quantity is going to be related to your balanced chemical equation. Right, so we would be able to take this delta H value here and say, well, 5 moles of propane would be 5 times negative 2,044 kilojoules. That's how much heat 5 moles of propane would release. All right. So real quick, let's look at this example. You have this reaction here. 2A yields AA. Delta H is negative 51 joules. What's the heat associated with the reaction of 6 moles of A? Okay, well, 6 moles of A is 3 times more than 2 moles of it. That means that the delta H should be 3 times more than negative 51 joules. And it is. All right, so let's look at this. An LP gas tank in a home barbecue contains 13.2 kilograms of propane. Calculate the heat in kilojoules associated with the complete combustion of all the propane in the tank. All right, so I have 3.2 kilograms of propane, and I want to know how much heat it would produce if I burned it all. And what I know is that for every 1 mole of propane, I'm going to release this much heat. Okay, so hopefully it makes sense to you then. If you take that kilojoule value, 13.2, not kilojoule, kilogram value, that 13.2 kilograms, and you convert that into a mole value, well, now you can figure out how much heat you'll burn, right? So I'm going to take my 13.2 kilograms, I'll convert that into grams, then I'll use my periodic table, and I'll convert it from grams into moles. Once I know how many moles that I have, then I can use my balanced chemical equation to figure out the delta H for my own burning of propane gas. Okay, so let's look at the steps here. All right, and this is all stuff that you guys already know how to do. 13.2 grams, I'm going to convert 13.2 kilograms, I'm going to convert it into grams. Then over in this step, I'm going to use my periodic table, and I'm going to convert my gram values into mole values. Then in this step, I'm going to be converting the moles of propane from the balanced equation to my moles of propane. So this is my balanced chemical equation step. And then what I'm left with over here is the amount of energy that I would have released by burning the 13.2 kilograms of propane, which is significantly more than what burning 1 mole of propane would give off. Okay, but it's the same step-by-step process that we've been doing stoichiometry-wise and dimensional analysis-wise. You guys are totally capable of doing that. We have another type of calorimetry we want to look at. This is called the coffee cup calorimeter, and this is going to be a reaction carried out at constant pressure as opposed to constant volume. Okay, the importance of doing constant pressure calorimetry is that we can relate that back to enthalpy. Okay, and in here we have the important relationship. Get my little writing thing. The Q of our reaction is going to be the opposite of the Q of our solution. Okay, so the Q of the reaction might be the actual process that's occurring, but the Q of the solution, that's going to be like us measuring the temperature of the water around the reaction and then using that temperature to find information out about the reaction itself. Okay, so whatever the change of temperature of the water is, we know that the opposite was happening in the reaction center itself. Okay, and when we have a coffee cup calorimeter, they're very, very straightforward. You have the 2 nested coffee cups. Okay, they're styrofoam because styrofoam is a good insulator, even though it's not environmentally friendly. And then you have some kind of, preferably a cork lid, because they are, again, it's nice to insulate with them. And you have a thermometer inserted, and you have this glass stirring rod that's inserted. And the glass stirrer is going to help us move around the reaction mixture to make sure that we have uniform temperature inside of the calorimeter. Right, so then we're going to have a measured amount of water inside of the calorimeter, and we're going to add a particular substance to it, right? With the thing, whatever it is that we're looking at. The temperature change that occurs is going to allow us to figure out the Q of the reaction that's happening, the dissolution reaction. We can then relate that, right, to our delta H value over here. Okay, so the Q of the reaction is going to equal the negative Q of the solution. And the Q of the solution we're going to be able to figure out because we're going to know the mass of the solution. We're going to know the specific heat of the solution. It's usually equivalent to the specific heat of water because we're looking at a lot of aqueous solutions here. And it's going to be multiplied by the delta T of the solution. So we're going to be able to measure all those things. Once we know the Q of the solution, we can say, all right, well, negative Q of the solution is equal to Q of the reaction. And Q of the reaction at constant pressure is equal to my delta H value. Okay, then to figure out your delta H value in terms of moles, we're going to do the same thing we did before. We're going to take our kilojoules and we're going to divide it by however many moles were present in our reaction. Okay, so let's take a look at this example. Once again, I'd hit the pause and I would try this out on your own. But I'm going to go through step by step. And again, first thing you want to do is organize your material here. Okay, so the 2 things that you need to do before you can proceed is you need to find all your information. Our problem told us that we could use the specific heat of water for our specific heat of our solution because it's an aqueous solution. Then we need to know the mass of that solution. Now, if I flip back real quick, it tells us here that I have 100 milliliters of the solution, and that my density of the solution is 1.00 grams per milliliter. Okay, those 2 pieces of information are going to be important for me to find the mass of my solution, which I need. So I can take that volume value and I can multiply it by the density, and that's going to give me the mass of my solution. So now I have my specific heat value, I have my mass value, I need to calculate my delta T value, final temperature minus initial temperature. Once I have all 3 of those things, now I can find the Q value for my solution. And that's just going to be MCAT, MC delta T. Okay, so 100 grams times 4.18 joules over grams degrees Celsius times 7.2 degrees Celsius. And my Q value is 3.0 times 10 to the negative 3 joules. All right, well, what am I going to do next? I want to find the Q of my reaction. Well, the Q of my reaction is going to be negative the Q of my solution. So the Q of my reaction is going to be negative 3.0 times 10 to the 3 joules. That's great. Now I want to find my delta H value in kilojoules per mole. So again, this is written out in 1 step, but you do not have to do this in 1 step. Okay, if you would like, you can do this step down here, separately, and you can figure out how many moles of magnesium there are in 0.158 grams of magnesium. Okay, and once you find that mole value, then you can take negative 3.0 times 10 to the 3 joules and divide it by the moles. All right, and when you do that, this is your delta H value then. Negative 4.6 times 10 to the 5 joules per mole of magnesium. Okay, and this, it says kilojoules over here, and the answer over here is in joules, but to convert that from joules into kilojoules, you would just be dividing it by 1,000. All right. Hopefully that makes sense. That's the end of this particular part. We have one more part left. Any of these concepts that you guys are not understanding, make sure you make a note of it and either send me an email or use our time tomorrow, Monday, 10:50 to 12:50 during our normal class time to have me go over more of the stuff for you. Okay?